Good afternoon and welcome to another Research in Action brought to you by the Division of Research at Florida Atlantic University. My name is Karen Scapinato. I will be today's moderator. With that, it is my great pleasure to introduce today's speaker. Dr. Masoud Lashaki is an assistant professor in the College of Engineering and Computer Science at FAU. He has 8 years of experience in the development of adsorbent materials for energy-related and environmentally driven applications. That's a mouthful, so I'm going to let him tell you what that is all about. Welcome.
Thank you, Dr. Scapinato, for the introduction. Hello, everyone. It is my great honor and pleasure to be here with you this afternoon. So today I will talk about different ways that we try to combat air pollution and our research activities here at FAU. So I always talk about the history of air pollution and pollution issue in general. So let's talk about old-fashioned waste disposal. So there was a book by William Haynes written in 1940s and 1950s. And it's a set of 6 books that he looked at the history of chemical industry in the United States. And then there's a fantastic quote that kind of, summarize our waste disposal practices back in the 1900s and early, in the 1800s as well as early 1900s. So the quote is, if we have something that we cannot make a profit out of, that's a waste. And the easiest way for the chemical industry to actually dispose that waste was down the river or up the chimney. If it was wastewater or solid waste, send it down the river. If it was air pollution, some smoke, some flue gas, send it up the chimney. So that mentality and those practices caused issues. And I provide a couple of examples of how those practices caused a big issue in a small city of Donora in Pennsylvania in the October of 1948. This is a picture of the city. You see the industrial stacks in the background. The city was in a valley. And then in October 1948, they experienced a very bad air pollution incident. On the right, you see a picture, and that picture was taken at noontime. So there was a thick, layer of smoke and pollution covering the city. And there were a couple of reasons for that. Number one, they had a strong temperature inversion, which is an atmospheric situation in which the pollution does not dilute into the atmosphere. It's trapped near the ground. And the pollution was coming from the activities shown on the left, zinc works, steel mills. So how bad it was? 6 days. The population of the city at that time was 14,000. Half of them, 7,000 got sick and 20 people died. So that was kind of a wake-up call here in the United States that we cannot continue up the chimney, down the river, such a kind of mentality. Another one is from London in United Kingdom back in December 1952. So there was some developments in the Middle East. The supply of oil was cut to the United Kingdom. They had to switch to coal combustion to provide heat and other applications, fuel combustion, as an energy source. And then it resulted in a very bad air pollution episode. What happened was they were burning coal. There was no pollution control or treatment in place, and they were releasing large amounts of particulate matter, PM, and sulfur oxides, as we call it, SOx. So they were releasing huge amounts of them into the atmosphere. And what happened was they also had a strong temperature inversion. Everything was trapped near the ground. How bad it was. The level of PM at that time was 30 times higher than the standard we currently have in the US. Sulfur oxide was 20 times higher than the current standard. So very bad. And this was not something that only happened once. In fact, if you look at history, this situation happened as early as 9th century. And in 1306, we had the first air pollution regulations issued by King Edward of England, and he banned combustion of coal in London because he wanted to prevent this situation. And this happened quite a few times. You see, these are the ones that has been documented with the number of people dying as early as 1873. We have numbers about hundreds of people dying. And this one was particularly very bad. During that 5-day period that they had this issue, 4,000 people died. Some people died after that because of complications coming from that air pollution incident. So the total death toll was closer to 12,000 people dying in London in 1952. These things were kind of a wake-up call for the global community that we need to change our waste disposal practices in order to prevent such incidents. Let me talk about a few success stories that we have had throughout the previous several decades. The first one is related to carbon monoxide. We also call it silent killer. Super poisonous compound, odorless, colorless. So if we are exposed to it, there is no way for us to say other than measuring it with some sensors. And that's why it's called silent killer, because people are exposed to it, they don't realize that, and they may die. A major source of carbon monoxide is from transportation and cars, because we have combustion in cars. And if the combustion is not happening in the right way, and if we have incomplete combustion, then we have carbon monoxide. That's why scientists came up with this idea of putting a catalytic converter in cars in the tailpipe. So carbon monoxide goes in and it's converted to CO2, which is a much less hazardous compound. And that resulted in us, over the past 4 decades since 1980, cutting carbon monoxide in the US by over 80%. So this is the national standard, and we are way below it. So the air we are breathing now with respect to carbon monoxide is way cleaner than the past several decades. So this is the first success story. But I want you to mention and look at the treatment here. Here, the pollution is generated, and then we treat the pollution with this catalytic converter. And that is one way to control air pollution. The second success story deals with prevention, how to do things to prevent air pollution in the first place. This is US electricity generation since 1970s based on fuel type. So in terms of coal, we peaked in the late 2000s. And since then, we reduced electricity generation from coal by 50%. Coal has sulfur. When you burn it to produce electricity, it will result in formation of sulfur oxides. So if we don't burn coal and phase out coal and switch to other fuels, we can control sulfur oxide emissions. The other thing is, look at the data about the sulfur content in diesel and distillate fuel. So back in 1994, 40% of the diesel in the US had sulfur over 500 parts per million. The other 60% was between 15 and 500. Now, 90% of it, and these are 2014 numbers, is less than 15, and a tiny bit of it, maybe 5–10%, is still over 500. So we removed sulfur from diesel and distillate and other fuels. And when you burn that, since there is no sulfur, you are preventing sulfur oxide formation. And that translated in this nice graph. We are here in terms of national standard, and we are way below it, all thanks to the changes we made in the type of fuels we use, and sometimes using cleaner fuels. So 90%, over 90% reduction since 1980s. The air we clean these days is much cleaner than the past several decades. The third success story, again dealing with prevention, was about lead. Lead is an element, and back in the 1920s, scientists found that if we add lead to gasoline in cars, it will significantly improve the performance and the combustion, and it will increase octane number. So they were adding it without really realizing that this is a very dangerous compound. Lead You put it in gas, it's super good in terms of performance, but when we burn it, we release it to the atmosphere, it accumulates in our bodies and it's super poisonous for kids because it prevents brain development in kids if they are exposed to high concentration over time. So that's why several decades ago, back in the 80s, they realized that, okay, that was a bad idea and we need to switch to other additives and replace lead in the gas. And that's why we have unleaded gasoline. And we add another additive called methyl tertiary butyl ether. This is the replacement, much more environmentally friendly and also not a significant hazard to humans. So as a result of that, this is the lead air quality situation in the US. We cannot even compare it with the 1980s. This is the national standard. And you see, we were exposed to super high levels back in the 80s and 90s. And 1996, this is where, based on Clean Air Act, the government of the US, tried to phase out leaded gasoline, switch to cleaner additives, but we still use lead because of its very good performance. If you look at racing cars, sometimes the different vehicles we use on farms, in airplanes, we still have a little bit of leaded gasoline used, but not cars on the street. The gas we get at gas station now is unleaded. And that is another huge success story, over 99% reduction in lead in the atmosphere in air quality since 1980s. So this is another prevention. If you don't put lead in the gas, you are preventing lead becoming an air pollution issue. So these are the success stories. So we have, we have been working, scientists around the world have been working on this, made significant progress. But the question is, what is the way forward? Because we are not done. We have had significant issues and scientists worked on it. And now we are trying to find new problems. And we have a ton of them. So we need to tackle and focus current issues. And that is the subject of my research, at FAU. Project number 1 is something called production of biomethane or renewable natural gas. So this is the first project that I'm going to talk about and how our activities is contributing to this field. A little bit of background, and these numbers are from the Environmental Protection Agency. All of us produce solid waste. In fact, an average person in the US produces around 5 pounds of waste per day. 5 pounds average per day, per person. 1/3 of this waste is organic waste, food, yard trimmings. By organic, we mean they can readily decompose. If you leave them even in the kitchen for a few days, you will see some liquid coming out of it, causing odor issues because they are undergoing decomposition. So they are very easy to decompose. 1/3 of the waste in the US is organic. The total waste, 292 million tons of municipal solid waste, MSW, 50% of it goes to landfills. So we put half of our waste in landfills. And part of that waste that goes to landfill, around 1/3 of it is organic waste. So part of the food waste, yard trimmings, which are readily decomposable, we put them in landfill. So now let's see the environmental issues coming from that practice. When we put it in landfills, we have 2 common issues in landfills. Number 1 is they release some leachate, or in simple words, we call it garbage juice. So this is the liquid waste that is leaching out of the organic waste we put in landfills. And we need to collect it and treat it, because if not, it will contaminate the soil. It will also cause issues in the groundwater quality. The other issue, which is the subject of our research, is the gas phase, which we call it landfill gas, LFG. And that gas is probably released to the atmosphere. What is the composition of that gas? 50 to 60% of it is methane. which is, by the way, natural gas. 30 to 40% of it is carbon dioxide. It is saturated with water vapor. And it has a very poisonous compound called hydrogen sulfide at around 100 parts per million. There are a bunch of other compounds, but these are the main ones, and they are of concern and they are of interest, depending on the way we look at it. Now, what happens if we do not control this landfill gas, if we just let it be released to the atmosphere? First of all, hydrogen sulfide is a very stinky compound, malodorous compound. It's the smell of rotten egg. So it's not pleasant for people living close to these landfill facilities to smell it. So we need to control it. We need to collect it because we don't want air pollution in the form of odor issues in our communities. Number two, the gas is mainly methane and carbon dioxide. Carbon dioxide is a very strong greenhouse gas, traps heat in the atmosphere. Methane is much worse than CO2 when it comes to trapping heat. Methane is 20-something times worse than CO2 when it comes to trapping heat in the atmosphere. So we really need to tackle it, because if we release it, we are adding to the current problem that we are facing with the greenhouse gases. That's why in some facilities, they collect it and they burn it, or as we call it, they flare it. They burn it, because if you burn methane, you will convert it to CO2, which is a smaller problem when it comes to carbon dioxide. On a apple-to-apple comparison, it's better to release carbon dioxide rather than methane. So that's why they just burn it sometimes. But it will cause pollution problem. You are going from methane to CO2, but then when you burn something, you have smoke generation. We have hydrogen sulfide burnt, converted to sulfur dioxide. That's another problem. So it causes pollution. You are treating something in some way, but we are causing other problems. And by the way, we are burning money with this practice, because half of this gas is methane, and methane is natural gas. So by just burning it and not making nothing out of it, you're burning money. So that's why we are proposing, and people have been practicing this as a more sustainable approach to handle this issue. And that means protect people, protect the planet, and make money. So this is the sustainable approach. And that's why these are EPA numbers. We currently have 550 operational projects in landfill sites across the United States to produce energy out of these landfill gas. Don't just burn it in a controlled manner to recover the heat and use it for power generation, for different things. And we have another 480 candidate landfills. This can be done, but not done yet. They are under consideration. Same concept is applicable to farms. In farms, we have organic waste, animal manure, crops, food waste. We generated tons and tons of these types of waste. And the practice is just don't leave them on the farm, on the field, so they go bad, decompose, and release air pollution. Put them in something called anaerobic digester, get something called digestate or a fertilizer, return it back to the farm to produce more food. And the gas phase is called biogas. This is, in terms of composition, very similar to landfill gas. 50-60% is methane, 30-40% is CO2. It has some water vapor, some hydrogen sulfide. So currently, we can just burn it as it is to produce electricity or heat. But the better way is to convert it to biomethane. And that is where we need purification. So we need to purify biogas to remove carbon dioxide, to remove hydrogen sulfide, to remove water vapor, and then convert this to something that is over like 97%, okay? Over 97% plus, methane. Then you can put it into the gas grid, or you can use it as fuel in cars or whatever application. This is a cleaner type of energy. And by the way, this is natural gas, but it does not come from fossil fuel. That's why we call it renewable natural gas, because as long as we have the waste, which is renewable, biomass, we always get some waste. So as long as we have the waste and that is renewed, you can always produce renewable natural gas. And this is not a fossil fuel, which are not renewable. The question here is, okay, we need to purify them. Landfill gas, biogas, similar in composition. One is produced in farms, one is produced in landfills, but we need to purify this in order to convert it to something that we can put in the gas grid. Now, currently, there are different technologies for doing this purification, but the main issue is they do it one at a time. Like they remove hydrogen sulfide first, then they remove the water, then they remove carbon dioxide. And ultimately what you have is the biomethane. Our question is, why not do all these at once instead of having 3 different processes back to back? That means a capital cost times 3, operational cost times 3. Why not do it all together? And that is called integration of the process integration. Put multiple things together and do it in one step instead of multiple steps. That's what we are going to do. That is the focus of one of our major research themes here at FAU, to integrate the purification process. Instead of 3 processes, do a single stage process. How we do it? We do it by using something called cyclic adsorption-desorption. So we do cycles. In the adsorption part, we use something called adsorbent materials, and it has a D, not a B. And then we put them in a bed, we send in the landfill gas or biogas, CO2 is removed, water vapor is removed, hydrogen sulfide is removed. The only thing coming out of the other side is biomethane. We purified it. At some point, our adsorbent can no longer accept impurities. It's saturated. That's when we go to the desorption stage. We heat up, so temperature goes up. We purge it, we sweep it with some purge gas like air, and all those impurities are coming out. The material gets cleaned, and then we can send it back to the adsorption to do this back and forth. This is the general idea. But the question is, what type of adsorbent we should use? There are a ton of different adsorbent materials out there, but very few of them work for this application. That's where we propose our hybrid adsorbent materials, which is a silica support, which is porous, and silica is inorganic. And then we functionalize our silica materials, which are porous, with something called aminosilins. I don't want to get too much into the chemistry of this, but this is a 2-step synthesis to make this material. We have the silica, we put water on it, hydroxyl groups, and then we add this primary amine in order to make our material, which is called aminosilica. Now, we have a number of questions to answer in order to have a checklist to make sure that this material works for our application. Does this material remove CO2? Yes. Does this material remove water vapor? Yes. We have a grant by Environmental Protection Agency. We have another grant on the same project by Janke Foundation. And we collected results over the past 1.5 years. And it shows that we can remove CO2, we can remove hydrogen sulfide, also water vapor simultaneously at the same time in one process. Is the uptake reversible? Yes. You can use it, saturate it, send to cleaning, back to the beginning of the line to do it again. Does this let the methane go through? Yes, the methane goes through. So 4 gases go in, only 1 comes out, which is methane. You recover and sell it. The other 3 are trapped. Is it thermally stable? Yes. Is it stable in air? Yes. So that means you can use this for hundreds of cycles without any loss in performance. Is it inexpensive? Yes, all these chemicals are commercially available. We make the material in lab in order to do this purification. The same material can be used for other applications. And that is where I go out to our second project, which we call it Air Revitalization in enclosed environments. There are a couple of words here that may not be common words that we use. So quick background. Enclosed environments are environments like space station, spacecraft, submarine, lunar habitats, because these are enclosed. They are not open to the atmosphere, okay? So these are enclosed environments. And you need different processes in place to ensure that pollution does not accumulate, because at home, if you have some pollution, you can open the door, you can have the ventilation system, and we get rid of the pollution. It's open to the atmosphere, it dilutes, but that's not the case in enclosed environments. Now, why we need air revitalization? We breathe all the time. We take in oxygen, we release carbon dioxide. In enclosed environments, if submarine crew, the crew in the spacecraft, astronauts, they inhale, exhalation contains carbon dioxide. It's not open to the atmosphere like on planet Earth. We breathe, the CO2 is diluted. It does not accumulate. But that is not the case in these environments, enclosed environments. What happens is gradually the level of the carbon dioxide goes up. At some level, you start to feel like you have headache, nausea, dizziness. At very high levels, it can kill people. It can make them unconscious. So that's why we should remove CO2 from these environments. And that is called air revitalization in enclosed environments. You need to filter the CO2 from cabin air. Now, NASA has a well-developed technology for this purpose, and they call it carbon dioxide removal assembly, CEDRA. And this is the process. What they do is they send in the gas from the cabin, they remove the water vapor first, and then they remove the CO2. And then the air goes back into the cabin, supplied so astronauts can breathe clean air. And then at some point, these beds, as we call them, are saturated. You need to switch to the second one while regenerating this one. So you send the temperature, you increase the temperature in order to clean that material. And you do cycles between the first one and the second. Now, can we improve this system? That's the question. Our preliminary results says, yes, there are multiple ways to improve this system. Number one, NASA currently removes these two compounds, water vapor and CO2, in two separate stages. So this is where water vapor is removed, and this is where CO2 is removed. Can we do it concurrently with another material? NASA cannot, the current system does not do it. Our material can do that, and we have preliminary data collected by multiple students showing that, yes, we can do it at the same time. Both NASA material and our material are very effective in removing CO2. Is the removal of CO2 fast? We call it kinetics, how fast CO2 removal happens. That's where our material is superior to NASA's material. We have done all these tests in details. Activation temperature. At the beginning of the process, you need to heat your material to clean it, to remove all these impurities on it, and that is called activation. NASA needs 200 degrees C for that. We only need 120 C, so we are cutting energy consumption. After it is saturated, you need to heat up again to remove CO2 and water vapor. NASA again needs around 200 degrees C for that. We need 120 C or below. Both materials are thermally stable. Both of them are stable throughout cycling. That means we can use them like many hundreds of times. And both of them are inexpensive. So there are some operational criteria in which our material is superior to what they are currently using. And this is very similar to the material we use in Project 1 for biogas and landfill gas purification. This is just a slightly different application. Project 3. In this one, we are going to tackle, and we are tackling, we have an active project with Florida Department of Environmental Protection, and we are going to tackle algal blooms. So Algae blooms, this is a very significant environmental issue here in Florida. So we have high levels of nutrients in surface waters because of use of fertilizers in part, phosphorus, nitrate, we have all these nutrients in surface waters, and then that is food for algae. So when the temperature goes up, they have lots of food, so they will grow out of control. And that is causing HABs, harmful algal blooms. And they cause problems for us. First of all, they are reducing the quality of surface waters. So that's a water pollution problem. When they go bad and decompose over time, they release toxins and also they cause odor problems. So it becomes an air pollution problem. It is also causing problems for economic activities. In Florida, the backbone of Florida economy is tourism industry. And if you have air pollution problem, you have pollution in the surface waters, that is kind of causing issues to attract people to spend money here, and create jobs for people. So this is a significant problem, and I'm sure many of us are aware of the significance of this topic. The proposed solution is we need to control nutrients, in this case, in our case, phosphorus in surface waters. If you deprive algae of food, you can control it. There are a ton of different ways, and I know Dr. Sullivan will have a talk on this topic in 2 weeks, but there are a ton of different ways to control this, but one way is to remove nutrients from surface waters. What we do here is called industrial ecology approach. Currently in the industry, we take resources, we make stuff, and then we dispose the waste. It's a linear economy. But the economy of the future, it's circular economy or industrial ecology. Like nature, there is no waste in nature, unless we add it. So one thing from waste from one process will become the feedstock for another process. So what we do is we actually make things, we use them, and then we recycle them. So it's a circular economy. Here, that concept is helping us tackle this problem. We are using the problem to solve the problem. And the way we do it is we collect the algae, we convert it to some adsorbent materials, and then use that material to remove phosphorus. So you use the problem, which is algae, to deprive algae of its nutrient, which is phosphorus, not nitrate. The focus here in our project is on phosphorus. How it works: we collect the algae, we do a very rapid energy efficient microwave heating in order to do some modifications in the structure of the algae, make activated carbon adsorbent materials out of it, and then we use it as an adsorbent. Surface water with phosphorus goes in, phosphorus will be removed, and clean water will come out. And that is it's just a proof of concept at this stage that we can do this and this treatment by using algae as our starting material. The same material that is collected and converted to some value added adsorbent material can be used for other applications. That can be used for treating a very well-known air pollution problem called volatile organic compounds, or VOCs. Quick background here. VOCs can come from wildfires, from plants, but it's mainly coming from anthropogenic sources, human activities. Paints, solvents, fossil fuels, they all contain organic compounds and volatile organic compounds. The gas we put in the car is a VOC mixture. A nail polish remover, it's a mixture. Many cleaning products at home is a VOC. When we go to a new house, the furniture, the smell coming from new furniture, that's formaldehyde, it's a VOC. And they are hazardous. At high levels, they can cause irritation in eye, nose, and throat. They can cause headache, nausea, Higher levels, they can cause damage to internal organs like liver, kidney, central nervous system, and it can also cause cancer in some cases. We have an additive here in the United States in the gas, like around 1% by volume, called benzene, and it's a well-known carcinogen. So it's very important to tackle this as an important air pollution problem. If we release VOCs, part of the issue will be public health. The other part will be VOC will react with another set of air pollutants called NOx, nitrogen oxides, and then they generate secondary pollutants, ozone, peroxyacetyl nitrate, PAN, and this is actually the reason that sometimes we have very bad air pollution problems in Los Angeles area. These two compounds, VOCs and NOx, react under sunlight, and then they convert to some secondary pollutants like ozone and other stuff. This is a picture from Los Angeles in 1950s, and you see the ladies in the picture are suffering from eye irritation because of the haze in the background. That's ozone causing problem. And this picture is from last year, September 2020. It was a combination of Los Angeles smog as well as some pollution from wildfires in California. And it caused a very bad Los Angeles smog incident it was so bad, it was kind of similar to the one they had back in 1994. So this is also a common problem. So VOCs should be treated, should be controlled to prevent this reaction. Now, potential applications for VOC. One of them is painting operations. During my PhD, I worked with Ford Motor Company on car painting operations. Each car in North America, on average, use 14.5 pounds of paint solvents. So, and then they do a series of treatments to control the pollution. My PhD research was done here. So we were developing materials, adsorbent materials, to control these VOCs. And the materials we make out of algae can be used for this purpose. So we not only use them for algae mitigation, we can also use it for VOC control in painting operations. Another application is evaporative emissions. We know that cars release pollution when they are running, but cars also release pollution when they are not running. The reason? We always have some gas in the fuel tank. In Florida, some days are pretty hot. The gas will evaporate. That's why we have this carbon canister in all cars to capture those fumes and vapors coming off the fuel tank. If not, it will get to the environment causing problems. And the materials we made out of algae can be used for this application in the cars to prevent pollution. And last application, this is Florida. All of us, many of us use leaf blowers, lawnmowers in order to, treat our backyards. So these are common things used in our communities. But the problem is we have made a ton of progress in many areas, but now not much of progress dealing with pollution coming from leaf blowers and lawnmowers. What happened is, based on in California, they predicted that in 2020, the VOC pollution coming from these guys, leaf blowers and stuff like that, may exceed VOC pollution coming from cars. And that's why sometimes when you pass by people working with these equipment, you smell some compounds, we smell, and those are VOCs. Some of them are carcinogen. So it's not only an occupational issue, an occupational health issue for people dealing with them, it's also an environmental issue and public health issue. Some eye-opening numbers. If we use leaf blower for 1 hour, the amount of VOC coming from it is equal to driving all the way from Los Angeles to Denver, 1,100 miles. Lawnmower use, 1 hour equal to driving from Los Angeles to Las Vegas, 300 miles. because we haven't done much of a pollution treatment or control here. We need to cut down pollution, and algae-derived materials that we made can be also used for this application. I want to thank our sponsors, Florida Atlantic University, Environmental Protection Agency, Florida Department of Environmental Protection, Janke Foundation for their generous support of our research activities. Also our collaborators, Solid Waste Authority of Palm Beach County, Orange County Utilities, Adrotech, and Hydron. And these are, we are actively involved with them in different projects. Before wrapping up the presentation, I want to have another overview of the significance of the air pollution and the activities we do here at FAU. We make environmental impacts by reducing air pollution like VOCs, hydrogen sulfide, greenhouse gas emissions, methane, CO2. We try to mitigate algal blooms. We try to improve air and water quality in communities across Florida. Socioeconomic impacts, if any of these ideas are commercialized one day, we are trying to valorize, add value to waste on farm, to algae. They don't have any value currently, and they are a big burden on the society, but we try to valorize them, give value to them, to create jobs. Green energy market is booming, and Florida should be part of this to create well-paying jobs. Broader impacts, we provide training opportunities for our young scientists and engineers. We try to have an inclusive workforce development, minorities, women, people with disability engaged in our research activities. And we try to form partnerships with industry to have reciprocal data sharing as well as stakeholder value propositions. Thank you very much for your attention. I would be very happy to answer questions.
Great. Thank you very much, Masoud. That was very interesting. And feel free to contact Dr. Lashaki yourself. He has his contact information right here. And just as a reminder, if you have any questions right now for him, please type the question in under the Q&A button in the bottom of your screen. A little pop-up comes up and you can type your question there. Masoud, you mentioned a lot of the resources on our the sources on where these pollutants are coming from, you know, and many of them are associated with our everyday life. But anything short of not mowing our lawn anymore or not driving our car anymore, what is it that we can do, you know, as the individual, as a public member of the community? What can we do to help with the air pollutant, to reduce air pollution?
Sure, that's a very good question. So there are multiple things that we can do. Some stuff are out of our control. It's on the industry. For example, about leaf blowers, our proposal is to put a filter made out of activated carbon on it, so that exhaust gas is not directly released to the atmosphere. That carbon filter can remove them and then send out a cleaner air. So that is on the industry to come up with the ideas. Like the car industry, VOC pollution from cars was a big problem. Now, by having catalytic converters, controlling painting emissions, by having carbon canisters, we are trying to tackle that. That is something that we should also do in the industry. Under personal life, there are multiple things. One of the reasons of VOC emissions is actually happening here in Florida is car idling. So when we are in the car waiting for something, the temperature is high, we are just running the engine without going anywhere. And those are exactly the times when combustion in the engine is not sometimes optimal, releasing pollution. That happens in a different form in colder places, like in Northeast United States, where in the morning in winters, cold start in the cars, and we have lots of these pollutions. So by having you know, newer models of cars, that is one. Our driving practices, not idling, using the cruise control, we can save like 5% on gas consumption by using cruise control. If we adjust the tire pressure on our cars, that's another 3-4% reduction in gas consumption. So these are things that we can definitely do in our day-to-day life to prevent pollution.
Great suggestions, Masoud. Okay, let's go to some of our attendees' questions here. Is anyone studying how to capture CO2 out of the atmosphere and incorporate into the purification process that you mentioned?
Yes, that's a great question. So before joining FAU, I was working at a company back in Canada called Inventis. They are now called Savante, and they are one of the very few companies commercializing carbon capture technologies. So at that time, we had active projects, and I was working with some Fortune 500 companies. Lafarge is one of the biggest cement producers in the world. They have active carbon capture projects, not yet at commercial level. They are doing pilot scale. Husky, Chevron, these are oil and gas companies having these CO2 capture projects, and that is mostly from existing sources. The companies I named, like Adsorb, that's another Canadian company, they are working in this biogas industry to remove CO2, to purify methane and sell it as new renewable natural gas. So there are companies working in this front, but we need, CO2 has no value currently. And that's a problem because when your product, which is CO2, has no value, there is not much incentive for people and companies to invest. So that's why, we need incentives, probably tax remissions from government. And for example, during President Trump, there was 45Q initiative. They asked companies, to capture CO2 and sequester it in geological formations, and they will give it like up to $30-40 per ton of CO2. So there are initiatives coming in, the new infrastructure bill coming in. So there are initiatives, and that will help speed up our battle with CO2 pollution.
Great, thank you. Coming back to the algae problem, how do you stop algae that are added to surface water from growing out of control? And that may be also a question for our speaker in 2 weeks when we're talking more about harmful algal bloom, but maybe you can address part of that question already.
Sure. So the big problem here, the root cause of this problem is over the past several decades, we had a boom in population and people are living at a much better situation. They have better access to food, but that came at the cost of using fertilizers. So in some parts of Asia, the use of fertilizer is 20 times higher than what it was in 1960s. Fertilizers, agricultural runoff, they get to the surface waters and end up in oceans. And that is causing problem because those nutrients, phosphorus and nitrate, are food for the algae. Here in the United States, Mississippi River watershed is a big problem because it comes from the agricultural heartland, capturing all those fertilizers and phosphorus and nitrate and bringing it to the Gulf of Mexico. And that's why where we have the red tide and the dead zone in the Gulf of Mexico. So one way to tackle this is to deprive algae of its food. So less fertilizers or better control techniques to limit phosphorus and nitrate in the surface waters.
It's a bit of a balancing act, right? Because the fertilizer is there for a reason as well, right? So it would have to be managed and somehow replaced, I guess, by other means if we wanted to continue what we're doing. Yeah, there is a question of whether the presentation is going to be available. The presentation today is being recorded, so it will be available on our website, FAU Research in Action. If you Google that, you should come up with a website. If not, please contact us. We'll be happy to share it with you. But in a day or two, you will see the presentation come up there. The next question here is, have you done any cost-benefit analysis of the algae-based adsorbent? And how does it compare with other adsorbents, such as conventional activated carbon?
For what application is this?
For the algae-based adsorbent.
Yeah, okay. So this is our first phase of the project. We haven't done any cost-benefit analysis, and we have commercially available activated carbon. So what we are doing is we are using them, we are testing them, commercially available samples, and then we try to match or exceed the performance of commercially available samples. But the main novelty of this research is we use the problem to solve the problem. So that is really the novel idea here, that you collect algae currently, people collect it, sometimes they put it into landfills. It decomposes, goes back into the environment like in pollution, leachate, landfill gas. So The issue is to valorize this, give value to algae. It's a big headache now, but we can give value to it by using it as a precursor, we call it, for producing and generating something.
Can you follow up a little bit on that? I know you mentioned that in your last slide, and that you want to put value on, for example, algae. What, how do you think algae could create value, the existence of algae? What would you use the algae for? I guess that's the question, to give it value.
So in this case, we are converting it to an adsorbent material. Like in my lab, we buy activated carbon. The other day, I ordered it, like a couple of pounds. We paid like $40 for it. So that is the value in the market. And algae, it's a big headache now. It's more like it's more of a problem, has no value. So if you make something out of it that can be used for environmental applications, that is why we call we are adding value to something, because we are using it as a feedstock. And that's the problem. We have these pollutions, no one is touching it because it has no value. They cannot make profit out of it.
Right. That's certainly true. And economic decisions often drive many of these problems. Related to that discussion, and is there any particular algae that would be better than other that would be more suitable for filtering, for example, substances?
That's a great question. There are different types of algae that we can use. We have started our initial tests with seaweed, because we are here at CTEC. We just need to go 100 feet to the beach and collect all this seaweed, at the coastline, and then use it. That's how we started our tests. Over the longer term, we want to use the blue-green algae, which is the elephant in the room. That's the bigger problem. And we want to see whether the same concept can be applied to that type of algae.
Great. Thank you. A couple of questions here related to moving the research into the commercial field and really the applied field, I guess, right? How far off do you think you are from implementing some of these solutions that you're talking about today on a mass scale across industries?
So we are not there yet. We are far from it, in fact. And the main problem is, again, in many of the, so if you have air pollution problems, and sometimes everyone is supportive because the pollutant is, for example, carcinogen. So everyone would like to control it no matter the cost. But then we have problems like CO2 that has no value. Even if you recover it, what do you want to do it with it? So that's why people are working on something called CO2 utilization, because we want to give value to the CO2. And unless we create value, that's why the government 45Q mentioned that capture CO2, sequester, and we will give you like $30, $40 a ton. That's why companies are working on enhanced oil recovery, where, for example, now you have sometimes oil wells, very old, losing pressure, you cannot produce any oil. They capture the CO2, and for each ton of CO2 you sequester in that oil well, you can produce 2 more barrels of oil. So that is kind of balancing the cost that you are putting into the capture. So it's kind of a collective effort here, how to capture CO2 and then how to give value to the CO2. We need applications, we need government initiatives. As part of the infrastructure bill, that was passed in Senate recently, there are billions of dollars coming into clean energies, and that may move things forward in a better way, that we phase out coal and we go after cleaner fuels like biogas, landfill gas, and try to add value to them. Initially, government initiatives, tax initiatives. Over longer term, cost would go down, and then we can make money.
And the problem with that is always that if you don't see it, there's no interest. And if there is no economic value to it, nobody is interested in it. Even with the carcinogen that you mentioned earlier, you don't see it then an immediate effect, right? Even if it's a carcinogen, the effect you'll see in like 20 years or so. So, that there's also not an immediate effect there.
One thing here, another initiative that the government can put, and we have it back in Canada, in the province of British Columbia, is now they have limits. By this year, we need X% of the natural gas in the grid must come from biogas and landfill gas. So by such things and such regulations, they are forcing companies to go out and innovate and find ways to make this happen.
Right. There's an
So we need that.
incentive for that then, yes.
We need a top-down approach sometimes.
Yeah. Okay, a very similar and very related question here. Which one of your projects are you most confident about it becoming commercial?
That's a very good question. My best hope, my best bet is the biogas landfill gas purification. We got a couple of grants recently. We got very good, interesting, preliminary data. We are working on publications. We are working for additional funding resources to work on different, fronts. So that is really my best hope, because the end product has a value. It's natural gas. You can sell it to make money.
Right, and funding is of course always a concern with research, because there's always very limited funds for it, and it takes a long time to get these funds. So by that time, technologies have moved on. So we are about out of time. I know there's one more question that is asking about how can we help prevent pollution. We already addressed that, right? No idling cars, the way you drive, and some other initiatives where you can just prevent gas, for example, getting into the environment, and the air pollutants related to gas, for example. I thank you very much, Masoud, for being our speaker today. Very interesting topic. If anyone has any additional questions, feel free to contact our speaker today.